Today, I'd like to talk about Vietoris-Rips thickenings, problems for birds and frogs. I think in applied topology, we use Vietoris-Rips complexes all the time. They are closely connected to various areas of pure mathematics, and those connections are growing stronger every day. So I think that's one of the points of this seminar, is to explore those connections. So let me explain my title. What are birds and frogs? I'm stealing this from an article by Freeman Dyson, who I believe died within the last month. So loosely speaking, birds are the type of mathematicians who view mathematics from a high vantage point. They can see lots of different areas, and they connect multiple areas of mathematics via theorems, broad theorems connecting formerly disparate areas that people didn't know were related. Frogs, on the other hand, get attracted to particular problems, interesting examples, counterexamples, and dig deep into those problems. So certainly this is a false dichotomy. All mathematicians do both of those things, but it's a useful perspective to have. Sometimes you behave as a bird, sometimes as a frog. Neither type of mathematician can thrive without the other. I typically think of myself as a frog. I get attracted to very specific, detailed problems. So I'd like to list at the end a lot of problems that I think might be attractive to frogs. And throughout, I'll try to highlight connections that birds might find inspiring. I was looking at this article recently. Actually, one of the advertisements at the end of this article in the AMS notices is this 2009 two-week workshop at the IMA, which was one of my first conferences I attended as a graduate student, and I think probably led to the thematic year at the IMA in 2013 and 2014, which then led to the AATRN seminar. Okay, so what is a Vietoris-Rips simplicial complex? You have two inputs, a metric space and then a scale parameter. Applied topologists think of the scale parameter as growing slowly when we look at persistence. Algebraic topologists might think of the scale parameter as going to zero. Same with shape theorists. Geometric group theorists might think of the scale parameter as very large. But in any case, you have a metric space, and you're going to build a simplicial complex from this metric space. So every point in your metric space is a vertex in your simplicial complex. So here I have about 20 different vertices because my metric space had 20 different points in it. If you have a metric space with an infinite number of points, like the circle, then you have a simplicial complex with an infinite number of vertices. Simplices in the simplicial complex are always finite. Here we have a k-dimensional simplex, which has k plus 1 vertices, whenever its diameter is at most your chosen scale. So the diameter of a simplex is just the length of the longest edge. So, because all three of these edges are at most my scale r, I include in this triangle. Let me increase the scale r a little bit. Because all pairs of these edges are at most, okay, yeah, sure. Because all pairs of edges are at most r, I have this simplex on 5 vertices, which is a 4-dimensional simplex. And as you increase the scale, the shape of this Vietoris-Rips simplicial complex changes. And one of the perspectives from applied topology is that you might try to approximate the shape of this data set by a Vietoris-Rips complex. So, if I thicken the data set more and more, I might get some spurious features. But there's a range of scales for which you recover maybe this circular homotopy type, which might be evidence that your data set was noisily sampled from a circle. Questions so far? A little bit of history. Where does the name Vietoris-Rips come from? Vietoris was an algebraic topologist. He invented Vietoris complexes for use in algebraic topology. So how do you define a homology or cohomology theory for a metric space? Well, you can try to turn that metric space into a simplicial complex, say the Vietoris-Rips simplicial complex, and then take a limit. So he took the limit as the scale was going to 0. Independently, Rips invented these complexes for use in geometric group theory. So one fact that Rips proved is if you have a delta hyperbolic group, think like a negatively curved group, and you equip it with the word metric, then the Vietoris-Rips complex of that delta hyperbolic group is contractible for all scales that are at least 4 times delta. And since you have a group, the group acts on the Vietoris-Rips complex, and you can use this to get a finite dimensional Eilenberg-MacLane space. I don't know the years in which Rips was working. Most of my knowledge of Rips's work is just in some papers by Gromov who cite Rips. So if folks know more about this history, please speak up or shoot me an email. Vietoris-Rips complexes have gained more usage now in applied topology. Using software packages, for example, the Ripser software package by Ulrich Bauer, scientists are computing Vietoris-Rips complexes on top of all types of crazy data sets these days. And that's good motivation, I think, for us to understand the underlying mathematical theory a little bit better. So let me give some background, as this is the first seminar of our series. So Hausmann's theorem is one of the motivational results in this area. So this is from the 90s. So if M is a compact Riemannian manifold, you can relax the compactness assumption. Then for all sufficiently small scales, and you can really say precisely what sufficiently small means in terms of the curvature of the manifold or the, roughly speaking, the injectivity radius of the manifold. For sufficiently small scales, the Rips complex of the entire manifold recovers the homotopy type of the manifold. So, in this Rips complex, here's my manifold, right? Every vertex in the manifold every point in the manifold is a vertex in my Rips complex. And then whenever I have, points close to each other, I have an edge. If I have 3 points close to each other, I have a triangle. So if I have 100 points close to each other, which you certainly do in a manifold, you have a 99-dimensional simplex. So this is a pretty wild beast, the simplicial complex. You have simplices of arbitrarily high dimension. So it's a nice result that for small scales, the Rips complex of the manifold recovers the homotopy type of the manifold. The proof, I would say, leaves a lot to be desired. And that's why I've put Verk's name here. So Giga Verk recently has given a nicer proof of Hausmann's theorem using nerve complexes. Thanks, Ulrich, for the history with Rips. So let me just say briefly how Hausmann's proof goes. Hausmann needs to choose a total order on all of the points on your manifold. So number your points in your manifold, from sort of smallest to largest. I mean, it's an uncountable number of points, but you get what I'm saying. And there's no natural way to order all of the points in your manifold. Then Hausmann is able to produce a map from the Rips complex down to the manifold. Vertices in the Rips complex go to points in the manifold. Edges in the Rips complex go to geodesics in the manifold. And that's why we need the sufficiently small so that you have unique geodesics. Triangles in the Rips complex map in as follows. The points in your manifold are ordered. So in the order, pretend there's 0, 1, and 2. Okay, between 0 and 1, you add this geodesic path. That's where one edge of your triangle goes. And then you complete to the triangle by taking geodesic paths from your first geodesic path. So if you reorder the points 0, 1, and 2, you get a different map. And then you can keep going to tetrahedra, etc. So this map is non-canonical, depends on a choice of total order of your manifold. And the inclusion map from your manifold back in is not continuous. Right? Vertex sets of simplicial complexes have the discrete topology. Manifolds do not have the discrete topology. So Hausmann has to do a lot of hard work to prove that this black map is a homotopy equivalence without even being able to construct a homotopy inverse. Applied topologists got more interested maybe by Latchev's result. You know, on a computer, you would never build a Rips complex on top of a manifold, but you would build a Rips complex on top of a finite data set. So what if your finite data set X in purple is pretty close to your manifold M? Well, if R is bounded from above by the curvature of your manifold, then you can always find a delta depending on your manifold M and your scale parameter R, such that if your finite data set is close enough to your manifold in the Gromov-Hausdorff distance, which is the notion of distance between metric spaces, then the Rips complex of your finite data set covers the homotopy type of the manifold. Okay, so this is motivating for data scientists. Take your data set, build a Rips complex, and in some cases, you can recover the homotopy type of your manifold. A lot of reconstruction results like this have been proven, many of them using persistent homology by many different people, you know, at least 10 to 20 papers that I won't try to survey here. I do think there are some steps in the proof of Latchev's theorem that folks in applied topology don't understand. And I do think it's valuable for us to figure out if some of those steps are wrong, and can we give counterexamples to some of those steps, you know, and I think it's worth going through. And if we think things we don't understand need to be understood better, I think it's important to do so. Foundational result for Vietoris-Rips complexes in persistent homology is a stability result. Earlier versions of stability had been proven by different people in different settings. But in this particular picture, if I take the Vietoris-Rips complex of the manifold, I'll recover, you know, the homotopy type of the manifold for small scales. And I'm looking at one-dimensional homology here. So in this two-hole torus, I have 4 loops. Okay, this two-hole torus, I have 4 loops. So I get those 4 loops in the persistent homology. Now, if you compute the persistent homology of this finite approximation, you'll still find these 4 long bars, but you'll also find some noisy bars, okay? And the stability of persistent homology generalizes this. It doesn't need to be a data set and a manifold. Just take any 2 metric spaces that are close in the Gromov-Hausdorff distance, and then their persistent homology barcodes of the Vietoris-Rips complex in any homological dimension are close in the bottleneck distance or this edit distance. So this is already a sign that metric geometry is appearing. So Gromov-Hausdorff distances appear, you know, in these 2 results. This is the main background I wanted to cover. Any questions? All right. So let me talk about one example that I think is quite nice. If you take the circle with the geodesic metric, path length metric, and unit circumference, we know what the homotopy types are. You get odd spheres. You get the same homotopy types, just at different scales if you use the Euclidean metric. And balls restricted to the circle. Or, yeah, never mind, if you just use the Euclidean metric. So, okay. So let's take the Rips complex of the circle at larger and larger scales. At small enough scales, Hausmann results apply. So Hausmann says you need to get the circle, even though you have simplices of arbitrarily high dimension, right? You have, you know, I can put 100 points that are really close, and so then I have a 99 dimensional simplex on those 100 points. The first change in homotopy type is at scale 1/3, And that's when these equilateral triangles appear. So not just this equilateral triangle, but an entire circle's worth. Okay. At that point, you might guess things become contractible forevermore, but a surprise happens and you get the three sphere, as I'll explain intuitively. And then this four-dimensional simplex has scale 2/5, so its diameter is 2/5, right? This is 2/5 of the way around the circle. When those regular four simplices appear, then you get the homotopy type of the 5 sphere. And then, as you get this simplex on 7 equally spaced vertices, then you jump up to the 7 sphere, etc. So you get all of the odd spheres for shorter and shorter windows of time until once you reach scale 1/2, that's the diameter of the circle, halfway around. Then you're contractible forevermore. Okay. Let me give you the intuition for this. So why should you believe this 3 sphere? So up until scale 1/3, think scale 1/3 minus epsilon, you have simplices of arbitrarily high dimension, but they form this thick infinite dimensional torus, okay? So I've drawn that here, this thick torus. One way to think of the 3 sphere, which we're going to use, is this 3 sphere is all of 3-dimensional space with a point at infinity attached. So just like the 2 sphere is the plane with a point at infinity attached, the 3 sphere is all of 3-dimensional space with a point at infinity attached. And we're going to visualize that as 2 solid tori glued together. One solid torus just sitting right in front of you, and then the other solid torus, or a circle's worth of disks, wrapping around in the other way. So think of all of these local simplices when the scale is prior to 1/3. Think of that as one solid torus sitting in front of you inside of 3-dimensional space. And then what changes at scale 1/3 is that we glue on this equilateral triangle, which sort of like fills in the disk, okay? But we also glue on this equilateral triangle, which is a nearby disk. And we glue on this equilateral triangle, which is a nearby disk. And as we keep gluing on all of those equilateral triangles, we get a circle's worth of disks that we've glued to our 3-dimensional torus. So we've taken one 3-dimensional torus, glued on a circle's worth of disks, another 3-dimensional torus to fill out the 3 sphere. And then if you take the 3 sphere homotopy type and glue on a circle's worth of 4 balls, then you get the 5 sphere. And if you take the 5 sphere homotopy type and glue on a circle's worth of 6 balls, then you get the 7 sphere homotopy type. So nice homotopy types, nice intuition that I'm happy to talk about further. The proof here is, well, it's nice in the sense that we use good machinery, code limits, homotopy code limits, but it's very combinatorial. So that the geometric intuition is not present in the proof that we give. Questions?
I have a quick question, Henry, if that's okay.
Yeah.
So what happens if you take sufficiently large, say, uniform regular samples around the circle?
Mm-hmm.
What do you see? I mean, so stability will tell you something about, which kinds of spheres appear, but do you have any idea of what actually shows up?
Yeah, definitely. So, and this is really the history of how we arrived at this. So Michael Adamaszek, in a paper in 2013, figured out the Rips complexes of equally spaced points on the circle. Okay, so those are completely characterized. They're always either odd spheres or wedges of even spheres. Okay, and then from that, you can figure out the homotopy types of an arbitrary finite number of points on the circle, even if they're not evenly spaced. You can dismantle dominated vertices to get down to an evenly spaced configuration, it turns out. Then from there, if you have a complete understanding of the homotopy types of finite samplings, you can use these tricks of colimits and homotopy colimits. So the Rips complex of the entire circle is the union or colimit of the Rips complexes of all of these finite subsets. Okay. And then we're in this setting of simplicial complexes. So all of these inclusion maps from the finite subsets into the circle are cofibrations. So the homotopy type of the union or colimit is the same as the homotopy type of the homotopy colimit. And then you can, show that once you sample enough points, the homotopy type stabilizes. So fix R, sample more and more points. Eventually the homotopy type stabilizes. It stabilizes as one of these odd spheres. And then this machinery of homotopy colimits allows you to say, well, once that homotopy type of all these finite things in your diagram stabilize, then the actual union or colimit or homotopy colimit has that same homotopy type.
Interesting. So just as a quick question, I'm not sure where between a frog or a bird this question is, but if you're working with a space in which there isn't such a nice way of regularly sampling, let's say even a sphere, do completely different techniques have to, is there a completely different approach, do you think?
Yeah, I think some of these ideas will be useful for the 2-sphere or the 3-sphere, and I'll say more about the spheres later, but new ideas will be needed as well, because it won't be as easy to get a complete characterization of Rips complexes of all subsets of the 2-sphere, Rips complexes even of arbitrary subsets of the plane, there's hard open questions about that.
Very interesting, thank you.
Yeah, thanks, Sankanan. I'm going to plow ahead, and I won't say too much about metric reconstruction, but Florian Frick, my collaborator, taught me this motivation. So you have a metric space, something like a circle. You lose part of that metric space. Maybe you lose some of the points. Okay, maybe you still maintain an infinite number of points. You want to recover your metric space. So you go to your corner store geometer and you say, please recover my metric space. So maybe one of our state-of-the-art techniques is to build the Vietoris-Rips complex. And if you're lucky, our expert geometer can recover your metric space up to homotopy type. Okay. A problem, and you should complain, is that the Rips complex is often not metrizable. So if the vertex set is finite, yeah, it's metrizable. But if the vertex set is infinite, then it's often not metrizable. A simplicial complex is metrizable if and only if it's locally finite, meaning each vertex is only in a finite number of simplices. But if you take the Rips complex of a circle, each vertex is in an infinite number of simplices. So Rips complexes of manifolds are not metrizable. They're not metric spaces. You can't equip them with the structure of metric space without changing the homeomorphism type. So with Michael Adamaszek and Florian Frick, we introduced Vietoris-Rips metric thickenings. Very briefly, how do you build this metric thickening? So let me edit some things for you. Okay. What I've written down here is just the definition of the geometric realization of a simplicial complex. The geometric realization of the Rips simplicial complex is all convex combinations of points, right? Where your points have to be simplices, they have to have bounded diameter, and this is just convex combinations, take barycentric coordinates. The Vietoris-Rips metric thickening has the same set, okay, but we're gonna equip it with a metric. We put the superscript M here to mean metric thickening. And think now of your points not as points, but as direct delta masses. Okay, so now a convex combination of points we've reinterpreted as a convex combination of direct delta masses, which is a probability measure. It's a convex combination, meaning it's a measure of mass 1. And you can put distances between measures. So Wasserstein or optimal transport distances. So what I have down below here for you is a picture where 1/3, 1/3, and 1/3 of these blue masses, think of that as the barycenter of this triangle in the Rips complex. And 1/3, 1/3, 1/6, and 1/6 of these red masses, think of that as a point in a tetrahedron, okay? And then the distance between that point in the triangle and that point in the tetrahedron is just the optimal transport distance. So you find the best matching and you look at how much work you have to do to move the blue piles of dirt onto the red piles of dirt. Okay. So for the birds, there's some measure theory and optimal transport coming up. Optimal transport is something that's, I think, important for all mathematicians to learn more about, particularly due to its relevance for machine learning. With this measure perspective, we can get a nicer proof of Hausmann's theorem. So we want to show that the Vietoris-Rips metric thickenings of the manifold are homotopy equivalent to the manifold. And now you can just map a measure to its Karcher mean. Okay, so this map going down is a little bit nicer. It's canonical. You map to a Karcher or Frechet mean. And the bigger point might be that the manifold now includes continuously back into the metric thickening, because the metric thickening induces the same metric that you had on the points of your manifold. Distances between direct measures, vertices up here is just a distance in the metric space. So we can now get a canonical map, and the inclusion is now continuous. And one composition is the identity on the nose, and the other composition is homotopy equivalent to the identity by a linear homotopy. So nicer proof. I really like metric thickenings, but I didn't have full motivation to talk about them, except very recently, my master student, and he'll continue on for his PhD, Michael Moy, has proved some really satisfying results. So if X is a totally bounded metric space, then the metric thickening and the Vietoris-Rips simplicial complex, they have the same persistent homology diagrams. So yeah, this is not yet up on arXiv, but it'll be in his master's thesis that he's defending this semester and on arXiv soon after that. If you think about persistent homology bars, the endpoints of the barcodes may change from open to closed, okay? Consequence of this is that the metric thickening is stable just because the Vietoris-Rips simplicial complex is, and an open conjecture is with the less than convention. So you include a simplex when its diameter is strictly less than R. Conjecture is that these homotopy types are always the same. Totally wide open, I'd say. Really interesting question. It's false with a less than or equal to convention. I'll keep going. I think the last main thing I want to do is talk about spheres, and then I want to advertise open questions. So what's known about spheres? I'm going to be using the Vietoris-Rips metric thickening. We know that you obtain the homotopy type of the sphere for sufficiently small scales. Up until the time when you glue in a regular simplex. So take the two sphere, the homotopy type of the Vietoris-Rips thickening, metric thickenings, or simplicial complexes is the two sphere up until you glue in this regular tetrahedron, okay? And more generally, the homotopy type of the Rips complexes or thickenings of the n sphere is the n sphere up until you glue in this regular n+1 simplex. With the metric thickening and the less than or equal to scale parameter, we can identify the next new homotopy type, okay, which I'll describe, but it doesn't, we can't show that it persists for any scales at all, which would be quite satisfying. So how does this work? So the circle, or sorry, the three sphere that we saw coming from the circle, you should think of that three sphere as a circle joined with a circle. So the first circle is just the space that we started with, okay? And then the join is, so the join with the circle is coming from the parameter space of equilateral triangles we glued in. Okay, so what am I saying? I'm saying that we had that the Vietoris-Rips complex of the circle at scale 1/3 plus epsilon. This was a three sphere, but you should think of that as a circle join a circle. The first circle was just the original circle you started with. And the second circle is a parameter space parameterizing the circle's worth of equilateral triangles that you glued in. So that's what happens for the n spheres. I'll talk this through for the two sphere. For the two sphere, the next new homotopy type is the two sphere joined with SO3 mod A4. SO3 mod A4 parameterizes the regular tetrahedra you glue in. SO3 tells you all the ways you could rotate this tetrahedra in three-dimensional space, and A4 is the rotational symmetries of the tetrahedron. So A4 is the alternating group on 4 elements, and that's the rotational symmetries of tetrahedron. So you again get the space you started with, the two sphere, join with this parameter space of filling simplices. You have these filling tetrahedra. How many did you glue in? Well, you glued in an SO3 mod A4's worth. We do not get any plus epsilon in scale. So we can't say anything about the Vietoris-Rips simplicial complex yet. However, Sungyuk Lim, Facundo Mamoli, and Osman Okutan can, in very recent work, relying on work by Mikhail Katz from decades earlier, who will also be speaking later on the seminar. So combining their work together, in the case of the two sphere, they can show the next new homotopy type for a range of scales. So they show you have a two sphere up until you glue in this regular tetrahedron. And then after that, you have this homotopy type up until you glue in this pentagonal prism. Okay. This pentagonal prism is 6 of the 12 vertices of the dodecahedron. So these lengths here to the cone vertex are the same as these lengths in the pentagonal base. Okay, it's sort of, it's sort of many distances are equal to the diameter here, as you might expect. For the birds, there's a lot going on here. So Facundo, Songyuk, and Okutan, and Osman, they connect this to quantitative topology and the filling radius of Gromov. They connect this to Kuratowski embeddings. And Facundo will be talking about this in next week. For people who like topological combinatorics, polytopes, there's a lot of polytopes going on here. And you might expect things like Platonic solids are going to appear for, the 3 sphere and the 4 sphere, or even the 2 sphere at later scales.
Did you make it yourself, or did you make the? Yeah.
This?
Yes.
Yeah, I made this myself, but I mean, I bought the pieces.
Yeah. Great. Nice.
Good question. All right, I need to wrap up. There are great consequences about these Rips complexes of n spheres. So Rips complexes of an n sphere, I mean, that's a good problem for a frog, but there's connections for birds. So the Borsuk-Ulam theorem says if you have maps from the n sphere to n dimensional space, if it's continuous, then you always can find 2 antipodal points that collide in n dimensional space. Okay, so classic algebraic topology. Almgren and Gromov and others have studied versions of this when you map into lower dimensional space. So there's something called the waist of the sphere theorem. And if you look at the pre-image of a point, you should be able to find a point that has a large waist. And they show that you can find a point whose pre-image is at least as large as the equatorial circle in this case. With Florian Frick, we've used results about Vietoris-Rips complexes of n spheres to get versions into higher dimensional space. So what can you say in the style of Borsuk-Ulam when you map a 2-sphere into 3D or 4D? Well, nothing necessarily collides because you could just include the 2-sphere into 3D. But we're able to give tight bounds on things like diameters. So we can find a small diameter set whose convex hull necessarily collides with the convex hull of its antipode, map to higher dimensions. So there's a lot of combinatorial topology showing up here. Carey-Theodori and Barvanok-Novick orbitopes. Orbitopes are generalizations of polytopes, except you don't have a finite number of points that you take the convex hull of. You might have an infinite curve that you take the convex hull of. The Rips complexes of a circle relate closely, we conjecture, to the faces of the Barvanok-Novick orbitopes. And these things are related to really important stuff in applied mathematics. So David Donahoe and others have studied why does the L1 norm actually promote sparsity. So super important topic in applied math. And it's related to things like the Barvanok-Novick orbitopes, or more generally centrally symmetric orbitopes. All right, so I went a little bit over, but I'll count in Elkanon's good questions in my time. I want to end with 12 questions for the frogs and just some final comments for the birds, and then we'll open it up to discussion. Open questions for the frogs. Yeah, Rips complexes of spheres at larger scales, I think is quite interesting, important. You know, maybe we'll never know completely, but the more we know, the happier we'll be. Check complexes of spheres or other spaces. So in a check complex, you're taking a nerve of balls. So think of the 2-sphere and then consider all balls of radius at most r. Okay, when the radii are small enough, the nerve theorem applies and you just get the 2-sphere back. But once the radius is large enough so that you get this, the homotopy type is going to change. And you know, I've thought about this, but we don't have any answers for what are the homotopy types of check complexes of spheres beyond the circle. We know the circle, but we don't know the 2-sphere, the 3-sphere, etc. Other manifolds, tori. So you should think of the torus with the L2 metric or the L1 metric. Ellipsoids. What are Rips complexes of ellipsoids? So even the 2-dimensional ellipsoid, or the 2-dimensional ellipsoid sitting inside of 3D is really interesting. I've worked on ellipses, but we can only get ellipses that are so eccentric. So take a circle and start making it more and more eccentric. We can only say anything really about ellipses up to eccentricity square root of 2. Once you stretch beyond that, you can't say much more. For these ellipses, instead of going straight from the circle to the 3-sphere, you get a 2-sphere in between. Okay, here's a pretty old open question. For any subset of the plane, is the Rips complex of that subset always a wedge of spheres? You can certainly get any wedge of spheres. Chambers, De Silva, Erickson, and Greist show that the fundamental group is free, which means you can't get a torus, right? The fundamental group of the torus is Z2. It's not the free group on 2 elements, which would be free. So this rules things out like the torus, but it doesn't rule out things like the 3-sphere cross the 3-sphere, okay? So can you prove that the 3-sphere cross the 3-sphere can't be obtained as a Rips complex of a planar point set?
Are you assuming that the complex is connected here?
I'm including wedge sums with the 0-sphere. So yeah. And then you can change the wedge subpoint, I guess. But yeah, you can get any you can get any union of connected components, each of which is a wedge sum of.
Yeah. Okay.
Okay. So take the integer lattice Zn. Equip it with the L1 metric, so the taxicab metric. For Z2, the grid in the plane, or Z3, the grid in 3D, Matt Zaremski and Brendan Mallory at Albany, they can show that the Rips complex is contractible once the scale is large enough. For the lattice in 4D or 5D, to our knowledge, no one can prove that it's contractible. And I mean, 2 weeks ago, I thought about this as hard as I could for a week, and it seems like it should be at your fingertips, and we have a lot of different proof ideas, but there's details to work out in all of them. Matt Zaremski has a nice paper connecting Basvina-Brady-Morse theory to Rips complexes. He'll be speaking later in the seminar. More generally, you should think not of this Cayley graph, the integer lattice, but the Cayley graph of other groups, hyperbolic groups, and Rips complexes and their homotopy types tell you things about the finiteness properties of those groups. Hypercube graphs, so take this graph, which is the hypercube in any dimension, just look at its vertex set, taxicab metric or shortest path metric, what are the homotopy types there? We can show that for scale 2, so for scale 0, you just get all the points. For scale 1, you get that graph, a wedge of circles. For scale 2, you get a wedge of 3 spheres, and we can tell you how many 3 spheres you get. Nothing is known for larger scales. So more generally, what are nice families of graphs that you can describe the Vietoris-Rips complexes of their vertex sets? Kasparovich, Gommel, Pervine, Sazdanovich, Bay and Yusu Wang and Ziegelmeyer have studied metric graphs where you have all the points along the edges of your graphs. And Giga-Verk has generalized their work to geodesic spaces where they're able to completely characterize the one-dimensional persistent homology of these spaces. But can we say more about k-dimensional persistent homology? Jose Pereira has a nice question about Rips complexes of this curve and the complex torus. It's related to his work on time series. Matt Cayley and Omar Bobrowski and many people study random statistics, but even for spaces like the circle, I think there's a lot more you can say from the statistical perspective. Metric thickenings are sort of measures of bounded diameter, but what could you say if you take all measures of some bounded variance on a manifold or even the circle? What are the homotopy types of measures of bounded variance on the circle? And how do those homotopy types change as you increase the variance? So Florian Frick and Fukuno Momoli have asked nice questions here. So have others, but I don't think anyone has worked on this, and it'd be nice to know the homotopy types when this changes for the circle, and do you get the 3 sphere, 5 sphere, 7 sphere again, or do you get something different? Looking forward, we'd like better Morse theories or more spot theories. So discrete Morse theory works great for finite simplicial complexes. Basvina-Brady-Morse theory can do stuff even for infinite simplicial complexes. But when you have the Rips complex of the circle, you want to have a more spot theory where you have the circle's worth of critical points or critical simplices that all glue in at once. Joshua Mirth has started exploring this in his PhD thesis, but I think there's going to be a lot of hard work here. Some of the Borsuk-Ulam theorems have been proven using characteristic classes by Michael Crabb, so connections to algebraic topology. Facundo will be telling us more about these connections to quantitative topology. And very recently, Berish Koskazuner has made some nice connections to geometric topology. So giving bounds on lengths of persistent homology bars, which is also done in this paper, using things like the thick-thin decomposition and other notions from geometric topology. So let me end there, and thank you for your time and attention. And I have lots of time. I can go past the hour and really interested in questions and conversation.
I would have a question, Henry. Can I ask?
Yeah, Teresa.
Why do you call the metric thickening? Like, is it just because the Vietoris-Rips complex is something similar to a thickening? Or is it also that it's a thickening of the Vietoris-Rips complex?
Great question. So it's not a thickening of the Vietoris-Rips complex, but it's a thickening of the underlying metric space. So a proposition is that this metric thickening is an R thickening of X. So what is an R thickening? So X is a metric space, and then an R thickening is a larger metric space that extends the metric on R. that extends the metric on x. And the r comes in because every point in the larger metric space has to be within distance r of the point of some point in x. Okay, so x is a metric space, and r thickening is a larger metric space that extends the metric on x. And every point in the larger space here, the Vietoris-Rips metric thickening, is within distance r from some point in x. So Gromov, in one of his books, he says, okay, let's talk about Vietoris-Rips complexes. For simplicity's sake, let's assume that x is discrete. Okay, and then he says the Vietoris-Rips complex is an r thickening of x. And that's true. Whenever your vertex set is discrete, you can equip the Vietoris-Rips complex with the metric, and you get an r thickening of your metric space. But when x is not discrete, you can't use the Vietoris-Rips complex, because then it's not even metrizable, right? So we sort of think of this space as an answer to Gromov's comment on, for simplicity's sake, assume x is discrete. You know, what if we don't want x to be discrete? What if we want x to be this circle, because our data sets in the limit converge to things like manifolds, right? So we sort of think of this as working in the shadow of Gromov, you know, trying to put down some things more precisely that Gromov has already thought about and you know, in many cases largely understood. Yeah.
Yeah, cool, thank you. That makes a lot of sense, thanks.
I have a question, Harry.
Yeah, Enrique.
Hey, so are all these x's, they can be the same, right? The xi's, sorry.
Sure, but you should think of them as different. Well, I mean, I'm curious why you say that. I mean, maybe I should write on the right-hand side that k is at least 0. So.
Oh, it's just like an edge, or like the support of an edge could also be the support of a 2 simplex and a 3 simplex and a 4 simplex.
Yeah, but right. Okay, so let's say you have this triangle where those top 2 points are the same, right? If those top 2 points are the same, well, their measures combine, and then it's just some. Yeah. I recently learned we have a mistake in our paper where we write k at least 1 here, which is annoying because we want the direct delta masses.
Oh, I see. Yeah.
So I was curious if you were sort of asking about that, but yeah. So take any finite number of points, 1 point, 2 points, 3 points, and then just take a convex combination of the direct delta masses on those points. Mm-hmm. So it's the same thing as a point in the Vietoris-Rips simplicial complex in the geometric realization, but now we have a distance between any 2 points in that geometric realization.
Mm-hmm. Thanks.
More questions?
Henry, I had a question about the, you have a metric in the metric thickening, and apart from metric reconstruction, are there any other like applications of this that you use this metric for?
Well, I mean, my main comment would be that you don't want to leave the category of metric spaces, right? When you take a metric space and make it bigger, you don't want to leave the category of metric spaces. You know, the work by Facundo Memoli and Seung-Yuk Lim and Osman Okutan is doing something very similar. So they use thickenings of this Kuratowski embedding. I mean, the proofs get a lot nicer when you stay in the category of metric spaces, I would say. They're able to prove a lot of nice things as consequences of their results. I don't know, are there applications of having a metric? I mean, I think of Michael Moy's results as really powerful. Michael Moy proves that you have the same persistent homology diagrams, whether you use the metric thickening or just the simplicial complex. And, you even more is true with the Kuratowski embedding. They already know you have homotopy equivalences. So that allows you to use simplicial techniques sometimes, discrete Morse theory, things like that, dominated vertices. Other times it allows you to use metric techniques or gradient flows, or maybe there should be nicer Morse theories. So if you care about persistent homology diagrams, you shouldn't be limited to just simplicial techniques. You should be able to use more geometry as well. So it's both in tools you have at your disposal and like morally, you should think of these thickenings we build as both simplicial complexes, but also metric space thickenings. Brendan, I don't know if I really addressed your question at all, but.
No, that's good motivation. Thanks.
I have a question and a comment about that.
Yeah.
So at some point I was thinking about these metric thickenings and having a continuous map from X to the thickening, for example, lets you pull back stuff on the metric thickening. For example, in some applications, I have like a vector bundle over a Vietoris-Rips complex, and I want to get a vector bundle on X. And I cannot do that if I'm using the usual Vietoris-Rips.
Ah.
And here X is some continuous space.
I see.
Like
I see.
Manifold.
So I see. So you're saying that vector bundles are sort of nicer on the space potentially.
Right. So basically the idea is you have a vector bundle on a sample and you want to get a vector bundle on the whole space. And from the vector bundle in a sample, you get a vector bundle on Vietoris-Rips, and then you try to pull it back to the original, to the space you're sampling from.
I see.
Like the basic idea of the. So like having the continuous map, that seems like a very nice thing.
Yeah, and maps in this blue direction are easy, and then the problem is that maps in this other direction are awful, because you can't just map X to X, because on the left in the metric thickening, X has its standard metric, like this metric on the circle. But then when you map it up here, you break the circle apart into an infinite number of discrete points. So Luis, that was sort of a nice comment extending on Brendan's question. Did you say you had another question and comment as well?
Yeah, so I'm very interested about this theorem of Moy.
Yeah.
Can you say something about why it doesn't work for the homotopy types? Like why does it only work for persistent homology?
Yeah, so let me tell you a little bit about how he proves this. And Michael, if you're here, please interrupt me and say more. So Michael gives an interleaving, essentially, between these. Really is that quite right? Really, he looks at finite subsets. So he looks at finite subsets of X. And then once he passes to finite subsets, he's able to get an interleaving. For any epsilon, you can get an interleaving using these finite subsets. And then it's sort of just like let your subset sample get closer and closer and closer, essentially. Michael, are you here? I think I butchered that a little bit.
So is it the
Yeah.
same? Is it the same persistent homology diagram, or is it interleaving distance 0, but possibly different endpoints?
Yeah, different endpoints for sure.
Yeah.
So I'm not talking about decorated diagrams.
Okay,
Yeah,
right.
and if you phrase this with persistent homology bars, you need to change endpoints from open to closed and vice versa. Michael, why don't you take a better? You can do better than I did.
Sure. No, I think you did fine. That's the basic idea. And I mean, the reason why it's not really talking about homotopy types at all is that getting an interleaving is a lot easier than talking about homotopy types. So this is largely based on just being able to build maps between metric thickenings, basically. And as Henry mentioned, it relies largely on moving to finite samples of X. So that's why the requirement is that X is totally bounded. And then in that case, there's a, I don't know if Henry mentioned this, but metric thickenings and Rips complexes agree in the topology with finite X. And that allows us to bridge the gap basically between metric thickenings and complexes.
Right. So this is already known for finite X, right? Yeah. So Michael, your microphone is cutting out a little bit, but yeah, Michael passes to finite subsets and gets interleavings between finite subsets. And once you have the finite subset, it's already known that these are homeomorphic even. So folks have to leave, I know, so please feel free to leave, but I'm happy to stick around to keep answering more questions or if other people have more comments. So more comments or questions?
I was curious about could you explain what the variance is for that homotopy type of all probability measures question?
Yeah, you bet. So, okay. So I think about the circle. So with the Vietoris-Rips metric thickening, we look at measures where the probability measures and the points have bounded, the points in your support have bounded diameter, right? So maybe you could have 1/3 of each of these points, right? And that's your measure. Okay. And then when does the homotopy type change? The homotopy type changes once you can get up to diameter 1/3, because at that point you can consider, measures supported on these 3 equally spaced points, right? So we sort of have all these measures filling this in. Okay, but so the first transition, so I'm interested either in finite measures of bounded variance or arbitrary measures of bounded variance. Okay, so an arbitrary measure, right? Don't think of it as like having points in its support. It's some little probability measure supported somewhere on this circle. Okay, so let's say I have something that looks like a Gaussian on the circle. So it has high probability on near the North Pole, right? So this point has high probability, but everywhere else it has low probability, right? So the diameter of this is the diameter of the circle, 1/2, right? But when my variance is small enough, all of the measures are going to be concentrated, right? So there's a measure concentrated near the North Pole. I have, some other measure that's concentrated near this point, right? Bounded variance means my measures are going to be concentrated near specific points, even if the support is the entire circle. That means that there should be a Karcher mean map. Take the Karcher mean map of these measures and you should get maps to the circle, right? So the red measure should map to its Karcher mean, this point on the circle. The blue measure should map to its Karcher mean, this point on the circle. And then you have the inclusion going backwards. So that's going to be a homotopy equivalence for measures of small enough variance. But as the variance gets larger, these measures are going to bleed out. These Gaussians are going to get thicker and thicker, and you're going to start having things that, I don't know, it could be a thicker Gaussian, or you'll have something like, Gaussians that are multimodal, or measures that are multimodal, right? So when does the homotopy type first change? My guess is that it's 1/3 that direct delta, 1/3 that direct delta, and 1/3 that direct delta. But for all we know, maybe there's a lower variance measure that changes the homotopy type first. So I think this is a great problem for folks to figure out. What's the first variance where the homotopy type changes? What are the measures that change that variance? For small enough variance, I don't think it's going to be hard to prove that you have the homotopy type of the circle. But once you get intermediate variance, how do you prove all the way up until this first critical variance that you always have these Karcher mean maps or other maps like down to the circle? So I think, I'm a frog, so I started with the simplest space I can think of, and frogs need to work this out. But once a frog works this out, then you can ask this on the 2-sphere and the 3-sphere, etc.
Would this maybe help with some sort of stability result? Like, I mean, the Dirac deltas are kind of close in some sense to these Gaussians that are centered at each of those.
Yeah, you know, like I would conjecture that the homotopy type doesn't matter very much, whether you're allowing arbitrary measures or finitely supported ones. Because yeah, you can approximate any measure with finitely supported one, you know, in some sense. So I agree with you. The homotopy type should be really exactly the same. Maybe they differ at endpoints of these persistent homology bars, but you know, stability. If you think about stability, that might be something to prove that the homotopy types don't change much, whether you look at arbitrary measures or ones with finite support. Whether you're looking at bounded variance or bounded diameter. Yep. In all honesty, I think bounded variance is probably the more fundamental important question than bounded diameter, which is the Vietoris-Rips metric thickening. And also, in all honesty, I would say that these check complexes are from some perspectives maybe even more fundamental. You know, nerves of balls on manifolds, once the balls no longer satisfy the nerve theorem, that's got to be really important, I think.
Hi, I have a question. So you had all of these theorems where the Vietoris-Rips complex recovers the homotopy type of some manifold or some geometric object. What I was thinking, I was asking myself if there is some theorem for the following situation. Let's say I'm having some experiment, maybe physical, like really physics perspective, and then the points of my data would form a manifold, right? Maybe an ideal world. But this manifold would sit embedded in some Rn usually, and then my experiment would have error, so that I'm actually not having a point process on the manifold, but rather in the embedding space, maybe with some Gaussian error in the direction of the normal of the manifold. And this would, to me, sort of seem like the natural way of phrasing things when I look at data from an experiment. And then I was thinking, is there some theorem which qualitatively tells me if my error is this large, I need this type of parameter R to recover the homotopy type?
Yeah, definitely. So I'll go back to these results here. So in Lotchev's theorem, M is a Riemannian manifold. And then X can be any space that's close in the Gromov-Hausdorff distance. So X doesn't need to be a subset. X can be sampled with error for sure. And then, you know, there are versions of this. So I'll say a couple of names just off the top of my head. Yogi, Smail, Weinberger. And then I think Chazal et al. You know, there are definitely versions of this where you're in Euclidean space. So your manifold, say, doesn't have the Riemannian metric, it has the Euclidean metric. And so there are versions of this in Euclidean space. And you can prove things like take a manifold, or more generally a set in Euclidean space with positive reach. So positive reach is sort of saying like it's not too curved, okay? And then, you know, sample nearby that set in Euclidean space. Then from the persistent homology of your finite sample, you can recover exactly the homology of the space you started with, the space that had high enough reach. And you sort of, and they give precise control over the scales you need to look at, which depend on sort of the reach of your shape, and they depend on how close your sample is. Yeah, so if you shoot me an email, I can send you some of these results. But yeah, people have definitely looked in this in the Euclidean context, where your point sample doesn't need to be a subset of your manifold, but just with Gaussian noise. And in this paper, they're looking at check complexes, but they really include in the statistical perspective. as well. So with high probability tending to 1, as something happens, the check complexes recover the shape of your manifold.
Thank you.
Yeah.
Hi, Henry.
Hey, babe.
I have a question over your thickening.
Yeah.
So in your formula, yeah, previous slide. Can I generalize it in terms of, because you're using a delta measure, right?
Mm-hmm.
Can I generalize it? And it sounded like it can, just by replacing the delta by a kernel. So, but I mean, in the sense that, you're saying that the Vietoris-Rips complex is not metricizable. And then if you put some measure and you sum over those measures, they are, right? I mean, in some sense, I feel like this is similar to a sense that where I just put a kernel and sum over the kernel and, related to kernel density, where you just say that I'm going to translate my space from something semi-discrete to something continuous, right?
Mm-hmm.
So in this case, if I kind of replacing that delta measure by any kind of kernel, I mean, it doesn't have to be like positive semi-definite or anything, but as long as any sort of kernel, including Gaussian, probably is the best behaved ones, but you can say ball kernel or triangle kernel, anything, as long as I now have a sort of continuous underlying space, this thickening will work, right? Is that
Definitely.
correct?
Yeah, definitely, because you can still, I mean, you still get these measures, right? And you can still do the Wasserstein or optimal transport distance between those measures. I think that's a really nice perspective, Bay, because here we're really thickening in the Vietoris-Rips sense, right? But if you put like a kernel here, you're thickening in a different sense. You're blurring in some other way, and maybe you want to change like diameter here or keep it, but you could put something like variance. Who knows? But yeah, I think you could do things like this result. You recover the homotopy type, or even better would be results like Lotchev's, right? So Lotchev's, you're not recovering a manifold. You're using a finite point set to recover a manifold, right? And the only Lotchev's theorems that we have for metric thickenings are complete cheats. And they're cheats because if X is finite, then the metric thickening and the Vietoris-Rips simplicial complex are homeomorphic. So we just use Lotchev's theorem for Vietoris-Rips complexes. But it'd be nice to have interesting new Lotchev's theorems for various thickenings and maybe the kernels, and maybe you don't want diameter, but something else there, might be really nice context to do cool things along those lines.
So yeah. So I want to extend that a little bit further, right? So in a way that, the reason I'm asking is because recently I've been looking at some kernel methods and I'm teaching kernel methods, and that's why it's kind of occurred to me is that your operation right now, right, is sort of thickening over the original space of where X sits, right? So somehow you are kind of extending from a discrete object to something continuous by putting measure. And if I just replace the measure by a kernel concentrated over the X, points in X, you achieve similar effect, except that you have a little bit more flexibility. And then of course you can also change how you define, replacing the diameter parameter by something else. But all those would be operating over some sort of extending the current metric space and make it slightly from discrete to continuous. And now if I'm going a little bit more extreme, that, maybe there is, the same way we can construct a Vietoris-Rips complex in the original data space, you can always construct it in the feature space through a feature map. Right. So the whole reason of people doing, this is completely something I just thought about it just now, that if I have point cloud that is in the original data space, the whole kernel machine is mapping those points to the feature space, where one of the original motivation is if my data point is not linearly separable, if I map it to the feature space, they become linearly separable. So now I don't think there's anything preventing you from constructing Vietoris-Rips complexes in the feature space. And I feel like that might be interesting open questions in that direction is what's happened when I transform through some kernel machine. This is the only similarity between that and my earlier comments is because I have the word kernel, but those are very two different things. Is that making sense to you?
Yeah, it is. You'll have to keep me up to date if you pursue this, because I'd be interested to see where it goes.
Yeah,
Cool
but
idea.
I'm just saying, like, I have not. I mean, it's just a transformation, right? But I have not seen people doing in that space, meaning that, maybe the Vietoris-Rips complex in the original data space looks pretty bad, but when I actually, using some nice kernel and map it to like reproducing kernel Hilbert space, that all of a sudden everything behaved better. I don't know. I have not seen work in that direction.
Thanks, Bei. More comments or questions?
I have one.
Yes, please.
So can you explain briefly the relationship to the geometric topology, thick and thin decomposition?
Yeah, I mean,
yeah, the very last page. Yeah.
Yeah, so let me pull this up. This just appeared on Archive this morning, and Beres Kuzkuzuner will be speaking a month from today on this. So I was really fortunate to learn a lot of this nice work with them. So let me try to get the link for you. Sorry, I should be trying to explain things instead of trying to find a link, but okay, I got it. So, all right, so I'm still, so if you check out this paper, you might have really good comments for us or corrections or improvements. So one thing that I know that you do in this paper is that you bound the persistence of any feature in the persistent homology by the spread of your metric space. Is that right?
Yes. Yes.
Yeah. And so here you're bounding all bars, right? I mean, besides it's an infinite zero-dimensional bar, but you're bounding bars in all homological dimensions at once, which is super powerful, right? So in this paper, Beres has sort of taught me how to take a different approach where you take a particular homology generator. So let's call, sigma is a generator of k-dimensional persistent homology. Okay, and then we'll bound the lifetime, the length of the bar. We'll bound that not by the spread of the metric space, but we'll bound it by invariance of sigma. Okay, so we'll bound it by things like the area of sigma.
So sigma is sigma comes from the underlying manifold, right? Underlying space X.
Think of sigma as a homology class, but to define like the area, we look at representatives. So we look at k cycles, right? So think of like a 2 cycle would be like a singular surface. A 3 cycle would be like a singular 3 manifold, etc. So we're trying to get more precise bounds depending on the depending on the homology class. So the thick-thin decomposition is related to this area bound. Our width results might be stronger, and maybe I'll let Beres say more about those. But so one comment is we're working in a very particular setting where we're working in unweighted graphs. Okay, so build a Rips complex on top of this unweighted graph. So you have a finite number of vertices. So it's much more particular setting than your work. Your work is mostly any arbitrary metric space. X is sort of the vertex set of an unweighted graph. So all edges in our graph have distance 1, and then the distance between 2 vertices is just the shortest path. But of course, when you build this Rips complex on top of this graph, you get this very high dimensional thing. So find a generator for k-dimensional homology. It's like this k-dimensional surface. And then find the representative in its homology class that has lowest area, which is just number of k simplices for k-dimensional homology class. Okay, and then the thick-thin decomposition comes up because, this, say, generated for 2-dimensional homology, it looks sort of like this 2-dimensional surface where you can certainly have pinch points and things. And then in geometric topology, they use thick-thin decompositions to say parts of our singular surfaces are thin, and then those collapse in the Rips complex just by sort of slicing in these ways. Other parts are thicker, and there you have to use, there's where the area bound really comes in to sort of fill these in.
Okay. So you mentioned spread first, but that is that means that there's some relationship between spread and this notion, or it is just a conceptual analogy?
Conceptual analogy. The relationship needs to be worked out. My summary so far would be, first of all, this was just posted on archive, so it's very new. Whereas your work has been more vetted. The spread is the bound that you use, and it bounds all homology classes at once, which is very strong. Here we use bounds which are particular to the homology class, and you're working with much more general metric spaces X. So far, we're working with vertex sets of unweighted graphs, although it'd be nice to try to generalize this, right? Like these ideas, maybe that's really what I want to say. These ideas from geometric topology, totally new to me, but it'd be nice to really work out how useful they are for Rips complexes of more general metric spaces.
Yep, thank you. Yeah, it looks interesting.